Welcome back to The Explainer. Today we're diving straight into the fascinating microscopic world of sugar. We're going to trace its incredible journey from a humble plant all the way to your palate, looking at everything from extraction and traditional sweeteners to the exact chemical reactions like supersaturation that make all your favorite confections possible. Let's get right into it.
To keep things moving, here's our roadmap for today. We'll hit history and sources, extracting and refining, liquid sweeteners, the chemistry of sweetness, and finally, crafting confections.
All right, Section 1, History and Sources of Sugar, the Roots of Sweetness.
It's honestly incredible to think about the botanical world tour of sugarcane. Saccharum officinarum, the hybrid grass we all know and love, started out in ancient New Guinea. From there, it spread to Indonesia and then hit India a few centuries before the Common Era. And actually, it was in India that the real art of sugar making was born. The idea spread like wildfire to the Mediterranean and eventually made its massive leap to the Americas post-1492.
And just to put that massive historical journey into a modern perspective, get this. India cultivated an absolutely staggering 281 million tons of sugarcane in just the 2004 to 2005 season. That is a mind-boggling amount of sweet stuff. It literally takes over 4 million hectares of land just to keep up with the domestic and global demand for this single crop. But here's kind of a fun botanical plot twist. While sugarcane towers over fields in the tropics and stores all that sucrose right up in its stem, we've also got the sugar beet. Sugar beets are grown in entirely different, colder, temperate zones, and they quietly store about a third of the world's commercial sugar completely underground in their roots. So, two totally different climates, two completely different biological structures, giving us the exact same chemical sweetness.
Section 2, Extracting and Refining Sugar, the Factory Journey.
So how do we get the sugar out of the plant? Well, it's a 4-step industrial process that basically forces the moisture out of dark acidic cane juice. First up, you crush the cane to extract this murky juice. Then you hit it with lime and heat to clarify it, which basically clumps all the impurities together so you can just skim them away. You take that clear juice, evaporate it down into a thick syrup, and finally, you spin the whole thing in a massive centrifuge. That physical spinning separates the beautiful raw sugar crystals from the dark, heavy molasses.
But in India, a huge chunk, we're talking 50 to 60% of sugarcane, never even goes through that final refinement. Instead, it becomes gur, or jaggery. And here's the real game changer with gur. It retains about 10 to 15% invert sugar. That invert sugar is like a superpower because it actively resists crystallization. It stays perfectly pliable, making it the absolute best binder for traditional treats like groundnut balls and coconut burfi.
And for all the baking enthusiasts tuning in, it's wild how much temperature dictates the physical behavior of jaggery syrup. Just a tiny bump in heat changes everything. Keep it between 110 and 120 degrees Celsius, and you've got a softball consistency that's perfect for puffed rice balls. Push it up 10 degrees to 130, and suddenly it's in a hardball state for burfis. Crank it all the way up to 145 degrees, and that exact same syrup becomes a brittle, transparent, glass-like material that is perfect for butterscotch. It is pure chemistry in action.
Now, when we look at highly refined solid sugars, the specific evaporation process dictates the form we get. You've got your standard granulated sugar, which is highly soluble and everywhere. Powdered sugar is just pulverized, usually with a little starch tossed in to stop it from clumping up. Brown sugar holds on to some of that molasses for a deeper flavor. And then there are incredible traditional forms like rock sugar, kalu sakare, where the syrup is slowly, painstakingly evaporated over days into massive crystalline slabs.
Moving on to Section 3, Liquid Sweeteners and Syrups, Beyond the Crystal.
Let's look at honey for a second. What's really fascinating here is that honey is mostly fructose and glucose, with only a tiny 2% sliver being sucrose. Why does that matter? Because that specific chemical makeup gives honey a phenomenal ability to hold on to water. It's the exact reason why a cake baked with honey stays perfectly moist and delicious for days longer than one made with standard crystalline sugar. Commercial liquid sweeteners, on the other hand, are highly specialized tools. Molasses is that dark byproduct packed with invert sugar. Maple syrup is literally just evaporated tree sap, where heat develops those complex, earthy flavors. But check out corn syrup. It contains about 30 to 35% dextrin. These heavy dextrin molecules act like microscopic traffic cops in your mixing bowl. They physically block sucrose crystals from clumping together, guaranteeing your candies stay perfectly smooth.
Section 4. The chemistry of sweetness. Laboratory transformations.
When you melt dry sugar, you trigger caramelization. You're not just melting it, you are fundamentally breaking the sugar molecules apart and forming entirely new organic acids. It completely transforms the sensory experience. You get a smooth, velvety structure, that distinct, rich brown color, and that wildly complex, pleasing aroma we all instantly recognize as caramel.
But supersaturation? This is the absolute core secret of the candy kitchen. It is basically culinary sorcery. When you boil a sugar solution and carefully cool it down without bumping it, you create a highly volatile, unstable environment. The liquid is literally holding on to more dissolved sugar than it scientifically should be able to at that temperature. In this state, there are millions of microscopic crystals just holding their breath, waiting to burst into existence the second you agitate the mixture.
The entire art of a confectioner is deliberately manipulating this chaos. If those crystals form too fast, you end up with a sandy, grainy candy. To stop that, candy makers throw in interfering sugars like glucose, or they use fats like butter and cream to literally coat the growing sugar crystals. This physical barrier stops the crystals from getting too big and guarantees that luxurious mouthfeel we all crave.
Section 5. Crafting the perfect confection. Application of science.
Let's bring this all together. Have you ever wondered why a lollipop is perfectly smooth and glass-like instead of crunchy and grainy? It's all thanks to liquid glucose and starch derivatives acting as master controllers of crystallization. They are intentionally added to toffees, bubblegum, and pan sweets to literally paralyze the sucrose molecules, freezing them in place before they have any chance to organize into large, grainy structures.
And we absolutely have to talk about confectionery fats because they are just as crucial as the sugar itself. Cocoa butter is literally magic in chocolate production. Because of its specific triglyceride makeup, it shrinks slightly when it solidifies, which means it pops out of chocolate molds perfectly. It has a brittle fracture point below 20 degrees Celsius, which gives a good chocolate bar that satisfying snap. But best of all, it has a sharp melting point right around 30 to 32 degrees Celsius, meaning it melts instantly and perfectly the second it hits human body temperature.
Local cooking traditions have to expertly navigate these chemical realities too. While cocoa butter has those incredibly rigid, perfect properties for Western-style chocolate, traditional Indian confections lean heavily on ingredients like ghee or vandaspati. These fats are incredible. They provide a rich structure and amazing aroma for local sweets. But they don't have the intense thermal stability of cocoa butter. That means in the brutal heat of an Indian summer, they can suffer from oil seepage or lose their shape entirely.
Ultimately, to borrow a perfect quote from our source, the essential component contributing to the texture of confectionery is the sugar crystal. Every chewy toffee, every single smooth piece of chocolate, and every crunchy brittle you've ever eaten is just a masterclass in controlling this one tiny, ancient crystal. The journey from a tall grass in a tropical field to the candy wrapper in your hand is paved with intense industrial extraction, extreme thermal manipulation, and some incredibly complex molecular science. So, I'll leave you with this. How much thought are you going to give to that microscopic architecture melting on your tongue the next time you unwrap a piece of cami? Thanks for joining me for this explainer. We'll see you next time.